Hello everyone, welcome again to Modeling Methods in Mechanical Engineering, and today we're going to start a new part of the semester, a new set of lectures that build on what we've actually covered in the first part, but we can actually have a point break in between, and we are going to start dealing or using the theories and identities and operators that we learned about in the first section of the semester to apply them directly to the solution of differential equations. And this is a part of the semester where we start actually diverting from analytical stuff to actual numerical approximation stuff. So we're going to be able to compare what happens when we pursue an analytical solution, if it's at all possible, to what happens when we actually try to approximate the solution, and what is the scheme and what is the framework for these approximations. How much can we approximate, how good is good, and how do we know whether we are approximating the right solution if we don't know the solution at all, which is the premise and the basis of actually trying to find a numerical solution. The fact that you don't know how to get the exact solution is what drives you to be able, or to figure out a way to find an approximate solution. So this being said, what I want to do here in the first lecture of this new part is to go over a review of differential equation, in particular ordinary differential equations. This is something that all of you have gone over and know, but I want to devote an entire lecture to synthesizing this into something that makes it useful for us. Now, the first thing we want to just take here, modeling methods in ME. And let's talk about ordinary differential equations. And we always use the acronym ODE for these. So what are these? Well, to begin with, let's just define what a differential equation is, which is, because believe it or not, something that's ubiquitous to engineering and science is differential equations. Sometimes, because it's so obvious, we fail as instructors to properly define. So when you took differential equations in your undergraduate education, you probably learned how to classify them. You probably learned how to be able to say whether there is a solution or not, whether the solution is unique or not, whether you probably be able to find the solution of certain classes of these differential equations. But you would probably fail to be told what is a differential equation to begin with. And why do we call them differential equations? Okay, there's differentials on them, on these types of equations, but what is the point? Well, the main difference between a differential equation and a regular equation is that the solution of a differential equation is not a number or a set of numbers. It's actually a function. So you're looking for a function. And an ordinary differential equation is one where you're looking for a function of a single variable. So this is a one-dimensional differential equation where the solution is actually a function, or maybe a family of functions that happen to be only in one dimension. And that dimension can be time, that dimension can be space X, or it can be anything. You're trying to look for a function that's a function of a single independent variable. Okay, so ordinary is the opposite. In the case of differential equations, is the opposite of partial. So in ordinary differential equations, you only see total derivatives because the function that you're looking for only has a single independent variable, and therefore partial derivatives do not exist. So that's what differentiates differential equations, ordinary from partial, and that is the main definition of differential equations. We're basically looking for a function, and that function can represent a field variable. In our case, that function can represent the temperature as a function of time, or the temperature as a function of space, or the pressure of a system, or the pressure as a function of time of a fluid at a particular location, or it can actually represent power, or it can represent speed. Whatever it is that the equation represents, the solution is a function of time or a function of space. So, in general, an order n, let me bring this here, an order n, linear, non-homogeneous, ODE is given as, so we can write an ordinary differential equation of order n as a combination of coefficients, known coefficients, and derivatives of the function that we're seeking. And in this case, we're seeking a function y, that's a function of t, right? And this is the nth derivative of that function with respect to t to the power of n. This is the coefficient Cn minus 1. So this is a general notation. All the way to the first order term. And the 0th order term is equal to some given function on the right hand side called g of t. Okay, so this is a general form of a linear, and we call it linear because it's a linear combination of derivatives of different orders and known coefficients. Those coefficients can be constants or functions of time, as you can see here, where time is obviously the independent variable of which this function y depends. We call it non-homogeneous because of this function on the right hand side. This independent term, also called the forcing function, is what actually sets the function, the equation different than 0. We call an equation homogeneous if it's equal to 0, therefore. And we call it, again, linear because it's a combination. And the order is pretty obvious. The order of a differential equation is the order of its highest derivative. So if the highest derivative in the differential equation is a third derivative of y with respect to t cubed, it doesn't matter if the other ones exist or not. That's a third order differential equation. Okay? So these C0t all the way to Cnt are the coefficients. Okay? If all the Ci as a function of t are equal to a constant, all of them, that's for I equals 0 all the way to n, then the ODE is known as constant coefficient. Otherwise is variable coefficient. So if at least one of the coefficients that linearly separate these derivatives is a function of time or a function of space, if the differential equation is a function of space, then we call this a variable coefficient ordinary differential equation. Also, if g of t is equal to 0, then ODE is homogeneous. Okay, and we'll explain a lot more of the repercussions and what would happen if an equation is homogeneous or non-homogeneous, if g of t is different than 0. And by the way, being different than 0 can just be a constant equal to 1. That already makes it non-homogeneous. All right, so there's a couple of things that are very important about in the theory of differential equations. First of all, the superposition theorem is a very simple theorem, but it's one that is going to help us a lot in trying to find the solutions of some of these. So if y1 of t and y2 of t are both solutions of the same linear homogeneous ODE, then y3 equals to a y1 of t plus b y2 of t. So we can construct a third solution, y3. Then y3 of t is also a solution of these ODE. All right, so this tells you a couple things. First of all, it tells you that a differential equation, an ordinary differential equation, a linear homogeneous ordinary differential equation, can have more than one solution, right? Because if I'm telling you there's y1 and there's also y2, these are two distinct functions who happen to be the solution of the same ODE, then I can take both of them and linearly combine them with any constant like that a or b, can be positive or negative, and then construct a third solution. And this third solution, y3, would also be a solution of that ordinary differential equation. So this is a very powerful theorem. Seems pretty simple, but we'll use it to construct very complicated solutions that otherwise will be wouldn't be accessible to what we're trying to do. All right. So what do we do if the differential equation is nonlinear? Well, then we cannot write it in general form like this, because nonlinear probably means that one of these derivatives or the function itself is appearing square or cubed, or the sine of y, or some of the derivatives are multiplying each other. So like y dy dt, for example, appears in the differential equation. That will make a differential equation nonlinear. Not the fact that it's being multiplied by a coefficient here that happens to be a function of time. That doesn't make it nonlinear. What would make a differential equation nonlinear is, again, the fact that the function or any of its derivatives would appear as powers, multiplications of each other, arguments of transcendental functions, or arguments of rational functions, or otherwise. Okay, so let's just confine them, so we cannot write it in general, because there's obviously an infinite number of possibilities of these types of equations. So let's just confine our studies to first order ODEs. Let's start with the simpler ones. And a first order ODE, remember, is one where the highest derivative is first order. And these first order ODEs, even though the highest derivative is only first order, actually govern a quite wide range of problems in engineering and science. Okay, problems that range from decays of radioactive material to epidemiology problems, all the way to the laws of electricity over Henry's law over an inductor, or Ohm's law over a capacitor. All of these are first order differential equations, and there's a lot of information that can be actually garnered from them. In general, a nonlinear, so now we're talking about nonlinear, okay? First order ODE can be written as, so what we're going to do is write it slightly differently, because even if it's first order, the fact that it's nonlinear means that we cannot just write it in a general form, because there's an infinite number of ways that we can combine. It can be the y can be dy dt can be to the power of 3 or 5, and multiplying y, or as an argument of anything. So we're going to write the equation like this. Somehow, let's say that we can isolate the derivative, being the highest, the first order. We're going to isolate it on the left-hand side. And on the right-hand side, we're going to write a function of y and t, where this function of y and t can be anything. And that actually describes the differential equation. And with an initial condition that we'll be referring to as IC, initial condition, which means that at time equals 0, we know what the solution is. We know the value of y, the solution that we're looking for, the function that we're looking for, at time equals 0. All right, and we use this little hat here to denote that that is given information, that's something known. Now, DODE, this one here, and initial condition pose what's called an initial value problem. IVP, sorry. So an IVP, initial value problem, is a combination of a differential equation and its initial condition, or conditions. There might be more than one. If the equation is of order 2, then we might need 2 initial conditions. If the equation is of order 3, then we might need 3 initial conditions. And we're talking about an equation of order 1, for which we only need 1 initial condition. So why is that? Why is the number of conditions actually dependent on the order of the equation itself? Well, let's think about this, right? A differential equation of order 1 is one in which the highest order derivative appearing in the entire equation is a first order derivative, like this one, dy dt. Now we know that in order to solve that equation, there will be some integration implicitly. right? Because in order to get to y, we're going to have to integrate the right-hand side. It might not be an explicit integration because this might not be integrable, plus we have y there, so we might end up with an integral equation. But somehow we're going to have to perform an integral, and it's going to be a single integral because this is a first derivative in order to find y. And when you perform an integration, a single integral, you can end up with a constant of integration, just one. And in order to fix one constant of integration, then you need one initial condition. Now, in the event that this were a second order differential equation, right, the second y dt squared, somehow in order to solve that equation, you need to perform two integrations. Implicitly, somewhere in the process of solving that equation, there will be two integrations. Whether you perform them or not, whatever method you choose to do has to have implicitly two processes of integration. And two processes of integration will lead to two constants of integration. And therefore, you need two initial conditions in order to fix that solution, to a single solution. All right. So that's the general form of first order ODEs. And so let's start classifying them. Let's start with the separable first order ODE. And the only reason why we separate or we classify them is because we're trying to find families of ODEs or forms or shapes of ODEs for which there is a method of solution. Because if I give you a generic ODE, even if it's a first order like this, chances are that there's no way to solve that problem. Okay? Even a first order ODE like this, that may seem simple. I can construct a function on the right hand side as a function of y and t. That makes it impossible for you to actually find, for any of us to find an exact solution to that equation. So the reason we classify them sort of in orders of difficulty, from easy to more difficult, of being able to find an analytical solution. When I say analytical, I use that interchangeably for exact solution. Okay? A method by which we can get an exact solution to this equation. So if the ODE dy dt is equal to function y of t, and by the way, f is given, so technically I should write a little hat on top of f, because f is just a function of y and t that defines the differential equation, is such that somehow it can be written as follows. So somehow I take that differential equation that is given to me, and it is such that I can break up the t's and send them to one side, and the y's send them to the other side, and separate them. That's why it's called separable. Then the integral of p dt is equal to the integral of qy dy. So obviously, if this function can be written like this, then if pt dt is equal to qy dy, then the integral of p of t dt is equal to the integral of q of y dy. That's no question about that. So we'll directly yield an implicit form of the solution y of t. So somehow, by performing this integration, we'll be able to get the solution. And an implicit form means that we might not get y of t directly, but we might get a relationship between y and t. That somehow is the solution of the problem. All right, so let's look at an example right away to see how this works. And again, this is old stuff for you. You've all been exposed to this and know what it is. I'm just synthesizing it, summarizing it, and sort of kind of giving it some direction that will lead to where we want to get. Okay, so let's say that we're given this equation with the initial condition at time equals 0, y is equal to 1. All right, so this is clearly a first order equation. So let's write it. First order, nonlinear. It's nonlinear because, as you can see, y is squared, right? So if y is squared or cubed, or the sign of y shows up, or y times dy dt or dy dt squared, that's already nonlinear. is homogeneous. So the right hand side is equal to 0, ODE. Now the fact that it's variable coefficient, which it clearly is irrelevant now that the function, that the ODE is nonlinear. As soon as it's nonlinear, the fact that it's variable coefficient or constant coefficient doesn't make any difference. So we can write this equation as dy dt equals f of y and t. Yeah, that one's easy. All we have to do is put the stuff on the right hand side, right? And well, we can see by inspection that f of y and t is simply minus 5t to the 4th y squared. That's it. All right, so this equation is already written in this general form. All right, now let's see if we can separate this equation. So attempt to separate. Let's see if we can. By the way, it's needless to say that not all ODEs, first order ODEs, are separable. Only a very, very small subset of them, in fact, are separable. And when they're separable, they're easy to solve. So I can take that equation, right, and I can attempt to bring the y's to one side and the t's to the other side. So because the right hand side is equal to 0, it's pretty simple. I can take dy dt is equal to minus 5t to the 4th y squared. And that means that I can bring the y squared over to the left hand side, and I get 1 over y squared dy is equal to minus 5 over t to the 4th dt. That is exactly the same equation as this one, which is exactly the same equation as this one. It's just written differently. All right. Now you can see that this here is q of y, while this here is p of t. So if I integrate the left and I integrate the right, so if this is equal to this, that means that this is also equal to this. Right? So, which means that I can take the integral of 1 over y squared dy, which is, well, y to the power of minus 2. That will be y to the power of minus 1 over 1. So this will be on the left hand side, we'll have y to the power of minus 1 over minus 1 is equal to the integral of minus 5t to the 4th, that will be t to the 5 negative, plus a constant of integration, c. So that means that y, and I'm going to say y of t to the minus 1 is equal to t to the 5 minus c. So I'm multiplying everything times minus 1 because of this denominator. And that will mean that y of t is the inverse of these. T to the 5 minus c. Now this right here is a family of solutions because of that c. Any value of c will give you a different function y that happens to be a solution to this differential equation right here. You can try it. You can pick any value of c here, like c equals 0, for example, take the derivative of that, plug it in here, and then take square of that times 5 to the t to the 4th, you'll get 0. Okay, so this is called its general solution. And it happens to be explicit. See, we put y as a function of t because we were able to separate this in this particular case. Otherwise, you'll get some sort of implicit solution. So if the initial condition says that y at 0 is equal to 1, then all we have to do is replace time with 0 and y with 1. So y is equal to 1 when time is equal to 0. Right? And then from there, what we get is that 1 is equal to 1 over minus c. And that means that c is equal to minus 1. So when we plug that into the equation, we get y of t equals 1 t to the 5 plus 1. And this is called the particular solution. Now, this one's general solution because it's general. It's a family of possible solutions. This is a particular solution because there's only one here, one solution that satisfies both the differential equation and the initial condition simultaneously. If you replace t with 0, you get 1 over 1, which is 1, which is what the initial condition says. And if you differentiate this and plug it in here, and plug y in here, you get that the equation is satisfied. So this is simultaneously the solution of the differential equation in the initial condition. This is the solution to the initial value problem. All right, that's simple. Let me make sure I can cut this in the right place. All right. Now, what if the equation is not separable? What if you can somehow give you an equation? By the way, the great majority of first order equations will be non-separable, right? You cannot just put all the t's on one side and all the y's on the other. There's another class that we call the exact first order ODE. The exact first order ODE. If the ODE is not separable, so the first thing you'll check is if the equation is separable. And if it's not, then let's write it. So we're going to take the equation, right? So we're going to take dy dt equals f of y and t. And we're going to write it as py t dt plus qy t dy equals 0. By the way, we can always do that. If I give you any equation in this form, you can always write it this way. And by the way, there's not just one way of writing it that way. There's actually infinite ways of writing it that way. So, just to be clear, any equation that I give you, you'll be able to write this way. It's not an if. So, now, then, if it happens that dp dy, the partial of p with respect to y, so the function that accompanies dt, you differentiate with respect to y, happens to be equal to the q dt, then the ODE is said to be exact. So now you have an exact ODE. Now, what is an exact ODE? For now, think of it as an equation that you cannot separate, but somehow you can solve very easily. All right? You'll see why. But in trying to interpret these physically, this is all mathematics, obviously, but physically, this is sort of equivalent to a field that is conservative. Sort of, and you'll see why at the end of this process of solution. This has a resemblance with a field, remember vector fields, that happens to be conservative, one that is irrotational. It's also now in differential equations called exact. Resemblance between the two. Now, if this is the case, therefore, a function u of y and t equals to a constant exists such that the function of y and t is simultaneously the integral of p with respect to t plus some function of y, because this is an integration with respect to t, then a function of y would be a constant. And u of y and t will also be simultaneously the integral of q of y and t with respect to y plus a constant g of t. Not to be confused with the right-hand side function and the non-homogeneous function of the differential equation. It's just a constant of integration, that because this is an integration with respect to y, this happens to be a function of t, also a constant of integration. And this is why exact differential equations happen to be analogous to conservative fields. And this function u happens to be the scalar potential that leads to that field. So if a vector field is conservative, irrotational, there exists a potential phi such that when we take the gradient of phi, we get that potential. We get that vector field. How do we find that phi? By integrating the elements of that field simultaneously. And this is what we're doing here. So the expression uy of t is equal to c. So we take that function that we find here, simultaneously the solution of these two. We equated. This function of y should show up on this side. The function of t should show up on the other side, and so on. We'll do an example in a minute. Then we equate it to a constant represents an implicit general solution to the ODE. Okay? So now we know how to solve it, if it happens to be exact. So let's go to another page and see. Example. So given the differential equation dy dt is equal to minus 2t plus e to the y divided by t times e to the y. So obviously, well, this is already written as dy dt is equal to a function of y and t, as you can see. This is a first order nonlinear ODE. Why is it nonlinear? Well, as you can see, y here, although it's not showing us as a power of y squared or y cubed or multiplying the derivative itself, it is an argument of a transcendental function. It's e to the y, right? That makes already this differential equation nonlinear. Not the fact that we could have e to the t here, that's just a coefficient. T is an independent variable, but the function that you're looking for itself appears as a power of another power of itself, appears multiplying its derivatives, or appears as a transcendental function of rational functions, or the argument of a transcendental function, like in this case. So is these ODE separable? That means, can we write it as q of y dy equals p of t dt? Well, the answer to that is no. You can try. I'm not going to go through attempts, but the answer to that is no. We cannot try to take the e to the y to the left hand side. Well, we can take this one here and take the dt to the other side. All right, but then we're stuck with an e to the y here, which we cannot separate. We cannot in any way take all the y's to one side. There might be a way, I'm not sure, but it is not. Is it exact? Now the next thing that you test is whether this differential equation is exact. Now let's write it as, again, this is something that we can always do. There's not a question of if. We're going to write it like this. I'm going to write the equation, this equation, like this. All right? So what I'll do is take this denominator, multiply it times dy, and take this dt and multiply it to the right hand side, and bring everything to the left. And what we'll have is 2t plus e to the y times dt plus t e to the y dy is equal to 0. So I've already written the equation this way. By the way, as I said, there's many ways of writing the same equation. I can multiply this whole thing by 2, for example, and it will not alter the equality. And it will be another p and another q. Anyways, this is p of y and t. As you can see, this is a function of y and a function of t, which doesn't need to be. In general, it's just p. It can only be a function of t. It can only be a function of y, possibly, or it can be a constant, for that matter. But in general, it's just a function of y and t. All right, now let's check, for these to be exact, the derivative of p with respect to y must be equal to the derivative of q with respect to t. So that condition needs to be met in order for these equation to be exact. So I'm going to take here and say the p dy, this with respect to y, well, obviously 2t, the derivative of 2t with respect to y is 0, and the derivative of e to the y with respect to y is e to the y. And I'm going to take dq and differentiate it with respect to t. So t times e to the y. When we differentiate with respect to t, well, this is just a constant multiplying t, and what will stay is that constant, e to the y. So yes, exact. All right? So that means that we can somehow find a function u of y and t, which is the integral of these with respect to t. So notice that in order to check whether it was exact, we differentiated this with respect to y, but now we're integrating it with respect to t. So we're integrating the left and the right, right? And simultaneously, the integral of these with respect to y has to match. There's such a function, u, that exists, that when we do this, it will show up. So the integral of 2t with respect to t is t squared. The integral of e to the y with respect to t is t e to the y. Remember, e to the y is a constant in the integration with respect to t. And because this is an integration with respect to t, this will yield a function y. That's a constant of integration. Any function y, when integrating with respect to t, any function y will represent a constant of integration. Now, when we integrate this one with respect to y, all we get is t e to the y. So if t is a constant, you can take out of the integral. The integral of e to the y dy is just e to the y, right? Plus a function g of t. Because it's an integration with respect to y, any function of t will be a constant. Now you can see that this function of t is right here. You can see that this function of y is right here, is 0. And you can see that these two are common between the two integrals. They have to be. Any function of t and y has to be common between the two. So u, y, and t is t e to the y, that common function, plus that function of t, and that happens to be equal to a constant. That right here is a solution. So t times e to the y of t plus t squared equals to a constant is the solution. And we're going to call this implicit general solution. It's implicit because, as you can see, we're not isolating y. And it might not be isolatable. In some cases, it's just that is a solution, a relationship between y and t, an implicit solution between y and t. In this particular case, we can take e to the y, right? We can take that e to the y, that's c minus t squared divided by t, right? And then we can say that y of t is the log of c minus t squared divided by t. In this particular case, we were able to find the explicit general solution. But again, that's not necessarily possible, and even if it's not possible, the solution is still correct. This is a solution to the differential equation. All right, let's keep moving. So now we are given an equation that is first order, and we first check whether it's separable. It's not. Then we check whether it's exact. It is, and if it's exact, then we integrate like this. So we know how to solve two types or two classes of first order differential equations, even nonlinear ones. Now, that's in no way a general method, because again, a very, very small subset of ODEs will be either separable or exact. So what if the equation is not exact? And we can come up with something called the integrating factor or integration factor, for that matter. So this is a trick that we play when an equation is not exact, but we figure out a function that we take and multiply times that equation, and it happens to make it exact. Okay? So given a non-separable first order ODE. That looks like P of y and t dt plus q dy is equal to 0. So we wrote it that way. We already figured out it's not separable. We cannot have t's and y's on either side of the equal sign. And then we check for exactness, and it happens that they're not. The p dy is not equal to the q dt, so it's not exact. And therefore, u of y and t does not exist. You cannot find it. If it's not exact, you can do that. You can try doing the integral, but it's just you're not going to find that common term in between the two, so that function does not exist. Now what we're going to try to do is seek a function f of y and t. I'm going to look for a third function. I'm going to try to make it up such that f of y and t, p y and t dt, plus f of y and t, q y and t dy equals to 0. Right? So it will be a function so that, well, if you come up with a function, you create an arbitrary function and you multiply it through the differential equation. Again, you're not affecting the equal sign. This equation is perfectly equivalent to this one, regardless of what f of y and t is. You're not changing anything. But the equation is going to be such that, or the function f that you're going to try to make up is going to be such that when you take the partial of fp with respect to y, you get exactly the partial of fq with respect to t. So now you've made this equation exact. So you come up with a function, you construct a function such that when you multiply it through the differential equation, you happen to make it exact. So if you do this, let's try to find f. Let's try to find f of y and t. Now, if I take the left hand side, remember this is a constraint. We are coming up with a new function and this is the only requirement. So I'm going to take this requirement and I'm going to say, well, I'm going to apply chain rules since f and p are both functions of y and t. I'm going to apply chain rule here. So this is going to be f times the p dy plus p times the f dy is equal to f times the q dt plus q times the f dt. Now you have this is a differential equation. Well, this happens to be a partial differential equation. See, you have first derivative. This is a first order partial differential equation. Now you have partial derivative. So these new first order partial differential equation, PDE, which we don't know how to solve yet, is more complicated than the original ODE. So this new equation is to find f, which is not even the solution of the equation. It's just to find f, which is a function that when you multiply through the differential equation, now you get an exact one. So this didn't help us in any possible way. But fortunately, however, in some cases, and again, this is in a small subset of equations that are not separable and not exact, we might be able to find an integrating factor. Cases we can restrict f to be a function of a single variable, i.e., we can say, well, let f be a function of y, or f be a function of t, right? It's a single variable. Simplifying the resulting PDE. That is, for instance, let f be a function of t, and let's see if we can somehow find it. By the way, this is not a general solution again. There can be, in some cases, ways in which we can restrict it to be a single variable function and then still find that solution, right? And I'll tell you when it works and when it doesn't work. So I'm going to take this differential equation up here, and if I say that f is just a function of t, this df dy goes away, and df dt becomes a total differential. So this will be f of t times dp dy plus p times df dt dy, which will now go to 0, is equal to f of t dq dt plus q df of t dt. So this will go to 0. This right here will become the f dt, total derivative. So we can take f of t as a common factor that multiplies dp dy minus dq dt, and that would be equal to q df dt. And I can send this dt over to the left-hand side, right? And this q over to the left-hand side, and then try to integrate df. So this will be, I'm going to flip this and put this on the left-hand side and this whole thing on the right-hand side. So this will be df of t is equal to df of t over f of t. Let's bring the f over to the left-hand side, this one, is equal to 1 over q dp dy minus dq dt times dt. So I took this dt to the other side. So if this is equal to this, so is the integral of these equal to the integral of these, right? And if that's the case, the integral of df over f is the log of f of t is equal to this whole thing, 1 over q, the integral of 1 over q, dp dy minus dq dt. All right. So I found f of t then is equal to e to the power of the integral of 1 over q dp dy minus dq dt. This is the integrating factor. So you might think that this solution process is general. So I take that function, multiply it times the differential equation, voila, I made it exact. But there's a caveat to this. This, we made the assumption that was a function of a single variable t. If somehow, when we put this factor in here, we end up with a function of y, we end up with any y in here, this integrating factor is not valid. Okay. This whole process is based on the premise that df dy is equal to 0. And if we end up with any y's here, so somehow dp dy minus dq dt divided by q, all y dependency has to cancel out in here. Whatever is in the numerator of y has to cancel out with whatever is in the denominator of y. Remember, p and q are the original functions that make up the differential equation. If somehow that happens, then we found the integrating factor. So this expression must be exclusively a function of t for the integrating factor f of t to be valid. Otherwise it doesn't work. Now if it doesn't work, then you make the other assumption, that you try let f be a function of y only. And if that's the case, then this one will go to 0. This will become the f dy, total derivative. You'll collect it the same way, and then you end up with an f of y that is an integral of 1 over p, dq dt minus dp dy, sort of the opposite, dy. And in that case, then it has to match a function of y to be able to be valid. All right. Now let's illustrate this with an example. Example. So given the ODE, and I'm gonna give it to you already written in this form. So it's already given in the form where we have P of y and t and Q of y and t. All right. So I guess we already determined that this is not separable. There's no way to bring all the y's to one side and all the t's to the other. Okay. Let me see. Or in fact, it appears to be separable. We're going to keep this as an example of a non-separable equation. So there's a way that I can take all the y's to one side and bring this 1 over t here to the left-hand side and try to integrate the cosine of over the sine of y squared and so on. This is definitely a nonlinear equation. Not only y is squared, but it appears as the argument of a transcendental function, a trigonometric function on both sides. So now we're going to check if equation is exact. All right, so we take dp dy is equal to d dy of 2 times the sine of y squared, and that would be 2. The sine of y squared would be the cosine of y squared times the internal derivative, which is 2y. So this will be 4y, the cosine of y squared. And when we do dq dt, we take the derivative with respect to t of t y cosine of y squared. And in that case, the derivative of these with respect to t, everything is a constant but the t, so that would be y cosine of y squared. So as you can see, even though the only thing that separates these two is a constant, is 4, they're not equal to each other, so it's not exact. So the p dy is not equal to the the q dt. So ODE is not exact. Okay, so let's try an integrating factor. Try an integrating factor of the form. Let's see if it works. Let's see if the f of t works. If not, we tried an f of y. F of t, remember, we found it to be e to the power of 1 over q dp dy minus dq dt dt. All right. So this is e to the power of this integral, not e times this integral. So let's see if it works. If it happens to end up being a function of t only, then this integrating factor works. If not, we try the f of y, which will be 1 over p. Well, we can do that from the equation that we demonstrated a bit ago. So this integrand here is 1 over q dp dy minus dq dt, which happens to be 1 over q is ty cosine of y squared, ty cosine of y squared, times dp dy which happens to be 4y cosine of y squared, and dq dt minus y of the cosine of y squared. So 1 over q dp dy minus dq dt, as you can see, we get 3y cosine of y squared on the numerator, and then that y cosine of y squared cancels out, so we get 3 over t. And this happens to be just a function of t. So the integrating factor will be possible. That's not yet the integrating factor. Remember that that we still have to integrate. So the integrating factor f of t is e to the integral of this integrand dt, which is e, the integral of dt over t is the log of t, so it's e to the 3 logs of t, which is e to the log of t cubed, and e to the log of anything is just that anything. So f of t is equal to t cubed. It happens to be a function of time only. So this is a valid integrating factor because it is just a function of t. That's the only reason why it's a valid integrating factor. So what I'll do is I'll multiply ODE by f of y. I'm sorry, f of t. We found f of t, we didn't find f of y. So I'll take the original equation, which is 2 sine of y squared, and then I'll multiply times t cubed, which is f of t, dt, and then ty cosine of y squared, and I multiply by this. So I seemingly didn't do anything to the equation. I just multiply by t cubed the whole thing. So the equation sign still applies. I just have a new p of ty, I'm going to call it p star, and this one is a new q of y and t. By the way, I've been using y and t instead of t and y, but that's okay, same thing. Alright, now let's check if the derivative of p cubed, p star with respect to y is equal to the derivative of q with respect to t. So this will be d dy of 2t cubed sine of y squared, which is 2t cubed cosine of y squared times 2y. So that would be 4y t cubed cosine of y squared. And the other one, dq star dt, is equal to d dt of this t cubed, and this t is t to the 4th y cosine of y squared. So if I differentiate this with respect to t, it will be 4t to the cube, and all of these is a constant. So I end up with the same exact thing, 4y t cubed cosine of y squared. So this is now equal to this. So the p dy is equal to the q dt. So ODE, the new ODE is exact. Exact. Great. So what do I do now? Let's solve it. So by the way, this is a star star. So this solution of this equation, by the way, this equation is the same equation as the original one. So the solution to this equation is the same solution to the original equation. It's the integral of p star of y and t with respect to t And u of y and t is the integral of q star y and t with respect to y. This will be the integral of this whole thing, 2 t cubed sine of y star dt, which is t to the power of 4 divided by 4, but with these 2 that will turn into a 2, sine of y squared, plus some function of y here that's a constant of integration. On this side I have the integral of t to the 4th of q, which is t times t cubed, t to the 4th times y, times the cosine of y squared dy. Okay, so in this case, this is the integral of the cosine of u times u prime. I'm missing a 2 here, so I can multiply times 2 and divide by 2. This will be t to the 4 divided by 2, and that will be the integral of the cosine of u times u prime. It will be the sine of u. That will be the sine of y squared. That's it. As you can see, this equates this, which is required, right? If this equation is exact, any function of t and y should be common between the two, and this function of t should show up here somewhere. As you can see, it shows up at 0, and this one should show up here as 0. So these are both 0, 0, 0. So continue here. The solution of the ODE is given as u of y and t is equal to a constant. So I take that function of y and t that I just found, including any constants of integration, t to the 4 divided by 2 times the sine of y squared is equal to a constant. And somehow, well, this is a solution. This is a general implicit solution. Can I find an explicit solution? Can I somehow isolate the y out of these? Well, let's try it. I can say that sine of y squared is equal to 2c divided by t over 4. It looks like I can. That means that y squared is equal to the arc sine, or sine to the minus 1, same thing, of 2c over t to the 4th. It looks like y of t is equal to plus minus the square root of, plus minus the square root of the arc sine of 2c over t to the 4th. And that looks like general explicit solution, or explicit general solution for that matter. It's explicit because now we have an explicit form of y as a function of t. It's general because we still have a constant of integration there that we can fix. If, for example, we're given an initial condition such that y of 0 is equal to some given y0, then we can find the particular solution. By the way, the particular solution can be found implicitly or explicitly. So if I'm given an initial condition, I can plug it in here, or I can plug it in here and still find the c. I can plug in whatever value of y I'm given and whatever value of t that's good for it, plug it in here and see what happens. In this case, an initial condition at time equals 0 will be no help, because at time equals 0, it would automatically make c equals 0. And if you make c equals 0, the whole thing goes to 0. So y is technically a trivial solution. 0 is a trivial solution. So I would have to be given a condition that is not at time equals 0, maybe at time equal 1 or something like that, for me to be able to find a non-trivial solution. So this is how it goes. All right. So again, you're given a differential equation that is first order, that is general, and then you first ask a question whether it's separable. Then after that, you ask a question. If it's not, then you ask a question, is it exact? If it's not, then can I find an integrating factor that is a function of t? Well, if no, then can I find an integrating factor that is a function of y? And if it's no, then that's it. You kind of run out of options. The only thing left to do is approximate the solution. Now, the subset of equations that happen to have a solution, either separable, exact, or one you can find an integrating factor, again, a very small subset of such equations. In general, you might not be able to get a solution. So the only thing you can rely upon is on these approximate solutions. So let me give you one last thing today. First order linear ODEs. First order linear ODEs. Now what happens is if the equation happens to be linear in its first order, it turns out that you always have a solution, no matter what. So if given the ODE written as, so the equation is written in this form, dy dt plus p of t of y of t is equal to r of t. Okay, so the equation is first order because the highest derivative is 1, the first derivative. Is linear, as you can see, y is not multiplying dy dt, is not square, is not the sine of y, or anything like that. It happens to be non-homogeneous because of r, and it happens to be variable coefficient because of p. Okay, the p can be a constant, that makes it an easier one, and r can be 0, that makes it even easier. It's just that in general it's a function of t. By the way, the fact that p could be, for example, an exponential function or sine or cosine doesn't make this equation nonlinear. It's just a variable coefficient that happens to be that way. It's a function of t, not a function of y. So this is a first order linear variable coefficient. Is variable coefficient unless p of t happens to be equal to a constant. Non-homogeneous. And unless r of t happens to be 0, that'll make it homogeneous. ODE. These ODE always, these types of ODEs always has a solution given in terms of an integrating factor. In terms of an integrating factor f of t and the particular solution y of t is unique. So one characteristic about linear equations is that the solution is unique, unlike the problem that we just solved, where we found that the solution is not unique. Even if you were to fix C with an initial condition or other types of condition, you still have a plus minus here. So you have two possible solutions. This one, because it's a linear equation, always has a unique solution. All right. So I'm going to take that equation and I'm going to rewrite it such that it appears like the ones that we've been trying to prove whether they are exact or not. So I'm going to take the p of t times y and minus r of t dt, multiply everything times dt, and then nothing multiplying dy. So you can see this is exactly the same as this, just written slightly different. This right here is p of y and t, and as you can see, this is q of y and t. Right? Obviously, the derivative of q with respect to t is equal to 0 because it's a constant. Q is equal to 1. So by default, this equation is not exact. But it turns out that if the equation looks like this, it comes from a linear equation, we can always find f of t and multiply ODE. So we can always find an integrating factor f of t, multiply times this thing, such that it becomes exact, such that this new P star of y and t and this new Q star of y and t are such that dp star dy is equal to dq star dt. So now it becomes exact. And it turns out that for these types of equations, f of t is always available. Now, let's try this. Remember that f of t, integrating factor, I'm not going to go through the whole process of showing where it comes from, but is e to the integral of 1 over q dp dy minus dq dt dt. And if we try to take the derivative of p with respect to y, and again I'm talking about star, 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 star. So the derivative of these functions with respect to y, notice all of these is a function of t multiplying y. So the only thing that I will have left is f of t times p of t. So I'm sorry, not star. It's just p, q. The star is the one after I multiply times q. So p. So I'm going to go back to the original one. So I'm going to take dp dy, and all I'm going to get is p of t, lowercase p. And then I'm going to take dq dt. Q is equal to 1, and then I'm going to get 0. So if q is equal to 0, or dq dt is equal to 0, q is equal to 1, and dp dy is p of t, then the integrating factor f of t is e to the power of the function lowercase p of t dt. So if I am given a linear equation that looks like this, we can always find an integrating factor to make that equation exact, no matter how it looks like, no matter what these coefficients are, if I take the integrating factor as the exponential of the integral of this coefficient p of t dt. So this right here is the general integrating factor for first order linear ODEs. Therefore, the ODE becomes, so I'm going to take this f of t and I'm going to multiply it here to make the equation exact, and here. So the new ODE is e to the integral of p of t dt, that's f, times p of t times y minus r of t times dt, and then plus f of t, which is e to the power of the integral of p of t dt times dy is equal to 0. So I can rearrange this, and this will be e to the power of p of t dt times dy dt. So I'm dividing and multiply times dy and dt, and dividing by dt, dividing the whole thing by dt, rearranging, plus p of t times y is equal to e to the power of p of t, dt times r of t. Okay, so I'll just rearrange that equation to make it look like the original one, just simply multiply times the integrating factor. So d dt, so I can apply a trick here, and this is equivalent to taking the differential of y of t times e to the integral of p of t dt. So do the math in the algebra, and you'll see that this right here is equivalent to doing this. You can take this chain rule. So the differential of these with respect to t is this times the differential of these, or the derivative of these, plus this times the derivative of these, and that's exactly this. and this is equal to e to the integral of dp dt dt times rt. And then I can say that this dy of t e to the integral of p of t dt is equal to e to the integral of p of t dt times r of t dt. And if I integrate both sides, the integral of this derivative is just y of t times e to the, then I can find what y of t is. So I'm going to take this to the other side as a e to the integral of p of t dt times the integral of e to the integral of p of t dt times r of t dt plus a constant of integration, the results of this integration right here. And this right here is the general solution for any first order linear differential equation, ordinary differential equation. So general solution for any first order linear ODE. All right, so let's do an example real quick for the remainder of the lecture. So I guess we can leave this example for practice in class, and then we just leave it up to here. We can work on this example later on. So this is it for today. So this was a crash course, a summary, a 1 hour and 15-minute summary of ordinary differential equations, and in particular solutions of first order differential equations, whether nonlinear, they will have to be either separable, exact, or accept an integrating factor. And if they're linear, this will be the way to get the solution. This is a general way of getting the solution to that equation. So thank you for your attention, and I'll see you next class.